Great. So today we're delighted to have our Simion Filip, who will speak about measure and topological rigidity beyond homogeneous dynamics.
Thank you for the introduction, and thanks to the colloquium committee for having me. So I'm saying this partially ironically because I'm part of the colloquium committee. So we really had to scrape the bottom of the barrel. But, in any case, I would like to report today on some joint work with many people. The main part that I'll discuss is joint work with Aaron Brown, Alex Eskin, and Filip Rodriguez Hertz. And it's part of a general direction of research where we're trying to generalize certain results that are known mostly for homogeneous dynamical systems to settings where there's no homogeneity or no Lie group, at least initially, as part of the data. And as an example, I'll mention hopefully at the end a work with Ben Lowe and David Fisher, where we kind of try to, so these are independent works, but the idea is that they're part of the same kind of framework where we try to obtain some rigidity results for dynamical systems that are not homogeneous. So I want to begin with one theorem which has the feature that it's simple to state. It's not the most general result that we can prove, but I think it has many of the main features of the results that we want to prove and some that we can prove to some extent. So the setting is that of a random walk on a compact manifold. So you have a compact manifold Q, you have a volume form on it, and you have several diffeomorphisms, at least two. And what you're interested in is assigning positive probabilities to each diffeomorphism. And now, starting from a point, you can roll a dice. It gives you a diffeomorphism with some probability. You apply that one, and then the second one, and so forth. And you keep navigating your manifold. And of course, so this is called a Markov chain or a random walk. And you can, of course, the volume measure is assumed to be invariant by each diffeomorphism. So if you start taking your particle uniformly at random, and the next step it will also be uniformly at random with respect to the volume. But more generally, to understand the long-term behavior of particles, you want to understand the notion of something called the mu stationary measure. So mu is this probability on the group of diffeomorphisms that is finitely supported, and we say that a measure on Q is mu stationary if it satisfies this equation. So what it means is, in words, is you take your measure nu, you apply the diffeomorphism, and you assign the new resulting measure weight pi, and you sum overall possible such steps, and you want to get back the original measure nu. So the measure nu is only invariant on average. It's not required to be invariant by the individual maps. So if it were invariant by the individual maps, this would be true. So if fi of nu was nu, then this would be true, but this is a priori a more general class. So maybe as an example of a measure which is which is stationary but not invariant, I will mention, if you take the middle third Cantor set, so if you take two diffeomorphisms, so F1 contracts everything to this interval, and F2 contracts everything to this interval, and then these two functions, if you keep iterating them, they'll essentially generate the middle third Cantor set. And if you assign equal probabilities to each such transformation, you're going to get the uniform measure on the Cantor set, on the middle third's Cantor set, and this is going to be a measure which is stationary but not invariant, because one iterate kind of collapses it to 1/2. Okay, so this is the definition, and now what is a theorem? So our theorem is that suppose you have a mu stationary measure nu on such a manifold. So assume it's ergodic. So ergodic simply means that you cannot decompose it into two pieces that are also mu stationary. And I'm making this assumption about, now notice this is on the measure on the group of diffeomorphisms. So suppose mu is uniformly expanding. So I'll define that, but it's just an assumption, can be checked in many examples. Then the first conclusion is that this probability measure nu is actually preserved by each transformation. And furthermore, under a slightly a stronger assumption, which is very closely related to this uniformly expanding, so not much of an extra assumption, the conclusion is that mu, this should say nu, this measure of the manifold is either volume or finitely supported. So there's only the volume measure or finitely many points which are permuted by each individual transformation. And furthermore, for every single point on the manifold, its orbit under the random walk is either finite or dense. So you either go everywhere or you're stuck on a finite subset. Yeah?
What was mu that we started with? It was
Sorry, this should say nu. Is that?
no, the second line.
Yes?
Is that the discrete probability?
Yeah, mu is the discrete measure. Yeah. So mu is on the group, nu is on the manifold. Yeah.
Will the same result hold as the measure is not discrete?
So most likely, yes. There's a kind of a we make this assumption on discreteness of the measure for kind of a technical reason. I think you can probably relax it much more than discrete or finitely supported. It's just kind of a technical assumption that is kind of orthogonal to the other difficulties in the proof. So in general, I think it should be relaxed too. Okay. So this is a statement about any manifold and any diffeomorphisms satisfying a certain assumption. So one remark is that this was proved in a special case when Q is the n-dimensional torus and DFIs are in GLNZ. And the assumption in that case, so instead of saying uniformly expanding, you would say that the group that they generate is Zariski dense, for example. So if you assume that it's Zariski dense, then this implies whatever uniform expansion means. And to get a non-trivial example of this theorem, you take a bunch of n by n matrices which generate a Zariski dense group, and then you smoothly perturb them to act as smooth diffeomorphisms of the torus that are no longer linear, and then they generate some God knows what kind of group, but they'll have this property of the orbits. So the orbits will be either dense or finite. Okay, so this is kind of a simple example of the theorem. So any questions so far? So overall, in the long term, we would like to be able to have versions of this theorem where you can have maybe weaker assumptions than what uniform expansion is. And the conclusion should be that your orbit closures are some submanifolds and the measures are some kind of smooth measures on those submanifolds. Yeah?
Actually, I didn't understand. How does, in the definition, how does mu play a role in that equation?
So the PIs, the probabilities.
Ah.
So I sample according to mu. Mu is a probability. So mu is given by these n probabilities. Does it make sense?
So it's a measure on the group generated by BFIs or on
No, on the support. So it's a finite measure on BFIs on the group diff Q. I mean, it's supported on the group. I mean, it generates a group, but it's not the whole group. So it's just on the generators of the group. Okay. So let me just very briefly say what uniform expansion is, and it's kind of what you might think it is. So for any D and any tangent space on the manifold, I take an orthonormal frame, and I consider for the number n, basically I take this frame, and I apply the random dynamics, and I take an expectation, and I see how much this frame has changed. So maybe think about just a single vector, just d is equal to 1. So you take a single vector and you randomly send it around, and you see how much it has grown. Okay? And you take a unit vector, so it's normalized, and you say the measure is uniformly expanding if there exists an n and an epsilon such that, in this case, let's say for every vector that you choose, any tangent vector, there's, if you iterate it n times, it has grown at least by a positive factor. Okay? So now if you do it 2n times, it will grow by at least a factor of 2 epsilon. Well, there's a log, so there's going to be epsilon squared and so forth. E to the 2 epsilon and so forth. Okay, and uniform gaps is kind of a variant on this condition, which says that somehow when you take these there's certain invariants which we'll come to called Lyapunov exponents. One, they have to stay away from 0 in some very kind of quantitative sense. But the upshot of this is that these are kind of conditions which at least you should be able to check in many circumstances without, sometimes even on a computer. So there's examples where you can check this numerically. So what I want to do in this rest of this talk is I want to maybe say a few general things about measure rigidity and what it is and what it isn't, because oftentimes you kind of don't know. If you're not in the subject, you don't know what you're fighting against. Somehow I'll tell you all the nice things that happen, but you don't know what are the bad things that could happen. And some general things about dynamical systems and hyperbolicity. And then a crucial tool that appears in a lot of the things that we do, which is something called normal forms. And then I'll state the main theorem, which implies what I said earlier, but also a bunch of other things. I'll say some of the things we are trying to do now, and also, what we hope to do in the future. Okay, so let me just give you something in dimension 1, a theorem that you've probably seen in the past, which is that if you have an irrational real number and you think of the alpha and you think of the translation on the circle by alpha, so thinking of the circle as R mod z, then you know that every orbit is dense. So the crucial word here is every. So in ergodic theory, it's a lot easier to get that almost every state, something is true for almost every point, but here, really every orbit of this dynamical system is dense in the torus. Furthermore, Weil showed that actually it's equidistributed. So if you take a segment of some length, then the amount of visits to that segment is proportional to the length of the segment. And here it's also a very special system. The only invariant measure is Lebesgue measure on the circle. So this is a very special system, but already has a lot of funny applications, so I thought I would show you one. So you've probably seen the following sequence many times. And so on. So this is the powers of 2. So what I want to pay attention to is the first digit of the powers of 2. So the question, if you've never asked yourself this question, is which digit occurs most frequently in this sequence? 1. So I think everybody says, and I promise it's the case that actually 1 occurs most frequently. And I claim that this is explained by Weil's equidistribution theorem. So if you've never seen this, this is so simple and so unexpected that I think it's worth trying to explain. So if I have k from 1 to 9 is the first digit of 2 to the n, if and only if 2 to the n belongs to the so there exists an m 0 such that so k times 10 to the m is the first number with m digits which starts with that, right? So to be clear. And so now if I take log and base 10, I get that n times log 10 base 10 of 2 belongs to log base 10k log base 10k plus 1 modulo 1, because when I take log 10 log base 10, this becomes just m. So after translation by an integer, I have to land in this interval. And so these intervals actually basically 0 to log 0, this is the same as log, and this is log 2, then you have log 2, log. So for they partition your interval 0 to 1 into 9 intervals, and depending on where n times this is your alpha lands, this determines your first digit. So that's basically the proof, and this is why the one occurs most frequently, 2 next, and so forth, and 9 is the least frequent. So a corollary, if at some point you get lost, you can try to also check that any finite sequence of digits that you could write down that's legal occurs as the first digits of 2 to the n for some n. So this follows from Kroneker's theorem that every orbit is dense. Okay. So this is an example of rigidity. So the theorem tells you that something happens for every orbit, for every point, and this is why we can get these kinds of nice conclusions. But there's another simple dynamical system on the circle, which is just the doubling map. So x goes to 2x, so it's kind of wrapping around the circle twice. Then my claim is that this system is essentially isomorphic to a much simpler dynamical system, at least simpler in appearance, which is you take a compact space, which is 0, 1, 2 elements, and you raise it to the power n. And so this is topologically homomorphic to the Cantor set. And so there's a map from this Cantor set to R mod z, where you think of the sequence of zeros and ones as the triadic base 2 expansion of a real number. And of course, a Cantor set is not homomorphic to the circle, so this map is at countably many points. It is 2 to 1 because 0.99999 is the same as 1.0000. And then you have countably many such gluings that you have to do to get from the Cantor set to get a circle. So this map is countable, it's 1 to 1 outside of countably many points, but outside of that is not really an issue. They are essentially the same dynamical system. And this doubling map corresponds to the shift where you take the sequence and then you move it to the left and then you drop or maybe say differently, just drop the first element and then move it to the left. So these two dynamical systems are essentially isomorphic, and as you can see, you can prescribe absolutely arbitrary behavior of an orbit of a point. So you can write any sequence of zeros and ones, and there will be a point which will realize that trajectory. And equally, there's no useful description of invariant measures, for example. So for this reason, the following question is still open and will probably remain open. At least I don't know how long we'll be doing math, but at least for us it will be open. So if you take the number pi and you take its expansion in base 2, is it going to be the case that any possible sequence of zeros and ones will occur? So you don't know. It's true for almost every real number, but pi is not an almost every real number. This is really a question about pi and not about this dynamical system.
Can somebody ask ChatGPT now? During the talk.
Yes, and be wrong.
All right, these are examples. So this is a rigid system, and this is a very flexible, and this is kind of much more typical of a genuine dynamical system. So here's what we kind of want to stay away from. So there's something called the standard map, which is a map of the two tors, which is given by this innocent-looking formula. Xy goes to this expression. K is a parameter, non-zero. So when k is 0, it's a linear map. It's not hard to understand. But as soon as k becomes positive, we have a vast amount of ignorance about this map. So we have no understanding of the structure of it. So you can see some orbits plotted here. So this is a pre-ChatGPT orbit. So picture. People have been looking at this map since the, I want to say, 60s or 70s, and they plotted these pictures, and there's still no good mathematical theory of this dynamical system. You can see these circles, so on which people prove using something called KM theory that your dynamics is conjugated to these irrational rotations. you know that there are regions where the dynamics is at least has these kinds of counter set like shift space structures, but that covers a very small fraction of your space. So in general, the dynamics of, there's not really a good description of the system. And so there's a famous open question, is that whether there's any value of k for which this map has something called a Lyapunov exponent, which is positive with respect to Lebesgue measure. So people think this is always true, but essentially no reason, no viable approach to proving this is known at this time. Okay, so what is hyperbolicity? Now I want to just give you some basic things about dynamical systems. So we're going to be interested in a space, most of the time a manifold, equipped with a flow. So I'm going to consider a one-parameter flow, and an invariant measure nu, usually ergodic and a probability measure. So a flow means simply that things compose. You can also say everything with discrete time. It doesn't make a difference. So the fundamental theorem in this case is that of oscillatics, which tells you that almost everywhere with respect to this underlying measure nu, there exists a decomposition of the tangent bundle. So this is a measurable decomposition. It's kind of an object very much outside of differential topology or other such structures. Basically, I want to identify first three subbundles: the stable, the center, and the unstable. So in the stable direction, you have the negative Lyapunov exponent. So these are vectors which, under the flow, they decay exponentially fast, given by these numbers lambda I. And in the unstable direction, they grow exponentially fast, and in the center direction, at least asymptotically, they don't grow they could grow or decay, but not at an exponential rate. So if you take the log and normalize, that limit is 0. So this is the basic theorem, and so these numbers lambda I are what are called Lyapunov exponents. So they tell you these asymptotic growth rates of vectors, and the systems we're going to look at, we need to assume that at least some of these exponents are non-zero. So if all exponents are 0, it's a very different kind of dynamical system. We kind of set that aside, but generally the expectation is that most most things that you would try to write down should have positive exponents unless there's some kind of obvious reason not to. In general, this is very hard, as I illustrated with a standard map. Nobody knows how to prove that the exponents are positive there.
Oh, can I ask a question?
Yeah.
So you have like the S, C, and U. So for is that like stable and unstable?
Yes, stable, unstable, and center.
Center. So for the vectors in the center decomposition, do they just get sent to 0 then?
No, so in the center, so the ones in the stable go to 0 and go to 0 exponentially fast.
Yeah.
In the unstable, they grow exponentially fast. And in the center, it simply means that if I push the vector time t, I take the log and divide by t, that limit is 0.
It's because it's e to the 0, so you're just multiplying by 1. So
Yeah.
those have eigenvalue 1.
Yeah.
Okay, thank you. Kind of.
Yeah, there's always a confusion between the log and the...
Right.
So these are the exponents, not the factors. Okay. So in the smooth case, when you have this decomposition, this is Q, a very old theorem of Hadamard and Perron says that tangent to this linear space, so even though the bundles are measurable, somehow, surprisingly, there exists a manifold which is tangent to the stable direction, and the same thing for the unstable. And the points on the same stable are characterized by the fact that if they're in the same stable, they converge exponentially fast into the future. And the unstable, they converge exponentially fast into the past. And so this is kind of just a fact of life. It's a very useful and important theorem. In the center stable direction, things are a little bit more complicated. In general, what you can try to do is you can try to build such a manifold. It will not exist in full generality. In most examples, it will not exist. What you'll get is a kind of a Taylor expansion of that manifold, and when you realize it, you know that every smooth function, so every Taylor expansion can be realized by some smooth function. So if you realize it by some manifold, points along that manifold, they will diverge, but not too fast. So you can kind of arrange it so that they don't diverge too fast. Okay, so let me try to make sense of some of these objects in the setting of homogeneous dynamical systems. So in this case, people consider a quotient where G is a Lie group and gamma is a lattice, so that's your manifold on which your dynamical system happens. And usually the kind of the flow that has hyperbolicity is given by a semi-simple element. So what you can think of is, here I'm using some notation from Lie theory, A is the Lie algebra of diagonal elements. So if you think of SLN R divided by SLN Z, you take a diagonal matrix in the Lie algebra. So in other words, a matrix whose sum along the, only non-zero entries are in the diagonal and they all sum to 0. So that's an X, and the adjoint representation of that matrix on the Lie algebra of SLN gives you stable and unstable subspaces. So eigenvalues, positive eigenvalues, negative eigenvalues, and 0 eigenvalues. So that's the Lyapunov decomposition. And in this case, the stable manifold is kind of a relatively simple object, is the exponential of a Lie subalgebra in the Lie algebra of the group. And this Lie subalgebra is also going to be nilpotent in this case. The center is going to be, the exponential of the Lie algebra of elements that commute with the generator of your flow. And, So here in the homogeneous setting, you're in a very special situation. The manifolds are given essentially by linear algebraic data. And not only that, you even have a center manifold, not just a center stable. And it's kind of a naturally well-defined object. So what people have done, and many people over many years, they've considered dynamical systems on this Gmod gamma and looked at measures or sets that are invariant under such dynamical systems. So what I think nowadays is the main theorems are kind of due to Ratner, but there's been a lot of work by many people. Is the case when you're considering a flow actually generated not by a hyperbolic element, but by a unipotent matrix, or nilpotent, so you exponentiate the nilpotent. And the theorems are very much similar to the theorem I had in the first slide for Weil and Kronecker, meaning that the conclusion is that the orbit closure of every point is a nice submanifold, and every ergodic invariant measure is also a nice submanifold associated to some Lie subgroup of G. So it tells you that all the orbits and all the measures are that you can think about associated to unipotents, they are very nice, kind of the exact opposite of what we saw, for example, for the standard map. And so this is kind of, at this point, a fairly complete theory. Somehow all the, many things are known about this system. There's kind of a related situation where you take large subgroups of diagonal matrices. So you have several flows that commute among each other, and this is in general a very rare thing to see in dynamical systems, to have two flows that commute. And so they admit also a lot of rigidity properties, and this theory, I think, at this stage is still somewhat not entirely complete. There's some famous open questions, but again, you have a source of rigidity. So what I want to say about both of these examples is that they're somewhat confined to the homogeneous setting, because the abelian one, because it's very hard to find flows that commute, or two transformations that commute. And the unipotent ones, they have an important, so they have zero Lyapunov exponents, and there, when you take two nearby points, they diverge at a slow polynomial rate, which is something, again, you see very rarely in general dynamical systems. But they still, this kind of offers you a nice blueprint to think about in other situations. So any questions so far? All right, so now I want to go back to a general hyperbolic flow on a general manifold. And one thing that is somehow surprising is that even though we're talking about general manifolds, it turns out that there are certain Lie groups that come essentially, I wouldn't say out of nowhere, but they come out of the dynamical system, and they happen to be there even though they weren't there originally. And it has to do with a certain special structure on the stable manifold. And everything that I say kind of, so I should have said maybe this earlier. in dynamical systems, there's a kind of a very useful fact, which is that whenever you have a theorem about the future, you also have a theorem about the past. And so whenever you have a theorem about stable manifolds, applying it to the reverse flow, you get a theorem about unstable manifolds. And just for definiteness, I'm going to talk about stable manifolds here, but there's kind of always two theorems, and you can also make them talk to each other. So one interesting aspect of this is that in homogeneous dynamics, everything was dictated by the tangent space, but on general manifolds, you have to look at higher order jets. And what you obtain is something called, goes under the name of normal forms. It's kind of the same idea as in Jordan normal form, where if you have any matrix, it says by changing coordinates, by conjugating, you can bring it to some specific form of a much simpler kind, which you can then study by explicit. Yeah?
Can you say again what jets are?
I mean, if you have a function, for example, it's like the higher order Taylor coefficients.
Okay.
So and then you can make a bundle out of that.
Okay.
Make a bundle. Any other questions? Okay, so what does this theory of normal forms tell us in this case? So again, on the stable, suppose you have these Lyapunov exponents, then it tells you that there's a certain geometric structure on the stable manifold. So maybe I should have drawn a picture. Oops. So if this is your Q, your manifold, you have these stable manifolds that kind of give you something like a measurable foliation. And when you look at the construction of the stable manifolds, usually what happens is that you kind of choose a chart and you try to represent them as the graph of some function, and that's basically how you show that they exist. But what Kalinin and Sadovskaya, building up on many previous works, basically showed is that you can actually reparameterize, so change coordinates essentially on a little piece of your manifold, in fact in compatible ways, so that if I take another point and take another chart, these things are kind of the transition maps belong to a very special class of transformations. So you have these parameterizations with the property that when you change charts from one point to the other, you stay within a group of certain polynomial automorphisms of Rn, which are called subresonant maps. And furthermore, the dynamics, so going essentially, so from this manifold, so I apply the dynamics, I end up somewhere here. And if I look at the dynamics in this chart, it's again given by a relatively simple restricted polynomial transformation. So let me give you a concrete example. So this is the theorem. So let's say that your stable manifold is two-dimensional, and you have two Lyapunov exponents. And so I have this kind of, you might have noticed. So I always think of these numbers as positive, but I put a minus sign here. Okay? So lambda 2 is greater than lambda 1, and lambda 1 is strictly greater than 0. So then what does it mean to have a subresonant structure on R2? So I have to give you a class of polynomial maps, and they're given by this kind of what's written here. So you can translate and rescale y, but in the x coordinate you can shear, and you can shear actually by different powers of y. But the number of the highest power that you're allowed to put in here is determined by your exponents. So you can check that if you compose two transformations of this type, they still stay of this type. So this is a finite dimensional Lie group. It acts transitively on R2. One thing that's maybe interesting is that the dimension of this group can be arbitrarily large even for R2, right? So if lambda 2 is much greater than lambda 1, you get a lot of terms here. So these are subresonant maps, and the strictly subresonant ones are kind of analogs of translation. So as I said, this is a unipotent algebraic group where now you don't allow this these scaling multiplications. So it's translations plus polynomial shears in one direction. So the theorem is that somehow if you choose these charts, first of all, changing charts is maps of this form, and the dynamical system is also given by simpler maps of this form. Okay. All right. So any questions about this? All right. So to state the theorem, I need to introduce a notion again associated to the measure, which is called. I want to talk about Gibbs states. So again, we have a general dynamical system. An important tool in studying these systems is to look at conditional measures. So again, you have this foliation. Sorry, it seems to be very little chalk. So you have this kind of measurable foliation, and you have some kind of mass. So what you can do is, on each of these manifolds, you can do some kind of Fubini type theorem where you, people call it usually this disintegration of the measure along this foliation. So you produce on each of these manifolds, so if you think of it abstractly, you obtain some measure. There's also some kind of transverse measure, and you can recover the original measure by kind of Fubini type formula where you integrate first with respect to each of these leafwise measures and then integrate transversely as well. So there's this notion of conditional measures, and it's a useful tool to actually study the original measure, because if you can say something about the conditional measures, and this
Sorry, Simion, are you trying to reconstruct the full view from just the measures on the leaves?
Yes.
Okay, and so. Okay.
So the first data is that you get these leafwise conditional measures, and there's also a transverse measure, but. And again, this is a kind of a purely local statement in the sense that you kind of work in a small neighborhood, and then, so these are kind of really foliations. So you have to be a little bit careful about how these measures are defined. But if you want, you can just cut your manifold once and just work with one chart. Okay, so you have these leafwise conditional measures, and the classical notion that people have looked. I guess maybe this is not quite the right term, but let's say that we'll call it a Gibbs state if this conditional measure is Lebesgue measure along the stable manifold. So our enemy in some sense is the things like the Cantor set measure, which is a fractal type of kind of object, and a Gibbs state in this sense is something that is kind of a smooth measure on the whole manifold. We're going to say that it's a generalized U-Gibbs state, so there exists also a notion of U-Gibbs state, but I'll skip it. If instead of requiring that your conditional measure is Lebesgue measure along the whole manifold, you require that there exists some family of directions along which you have this Lebesgue class invariance. So in order to state this precisely, you have to talk about these groups of strictly subresonant transformations, and you want to have some kind of invariance under a group. And the reason why you expect to encounter such kind of measures in nature is that if your measure nu is trapped inside a submanifold of your ambient manifold, so you have Q and there's some submanifold S, then the full tangent bundle is too large, the full unstable manifolds, but you'll have in some distinguished directions, you'll have Lebesgue class measures. So these U-Gibbs states are meant to capture this kind of possibility that you are of Lebesgue class and only a few directions, not in all directions.
Why are these called Gibbs states?
I think this has to do with Sinai in the 70s, who was transferring.
Did Sinai use the term Gibbs state for something like this?
Yeah, I think what, he introduced Gibbs states for certain measures on manifolds in kind of analogy with the ones from statistical mechanics. And I think sometimes these are also called SRB measures for Sinai, Ruel, and Bowen. But then once you get into these more refined notions, I think people stuck with U-Gibbs states, which it is what it is.
Okay.
A long story.
Yeah. Yeah. So the precise definition is a bit technical, but the idea is that you should think of this as measures which have some kind of extra invariance in only some of the directions. Okay, so so now I can state the main theorem, and what's interesting about this main theorem is that it's true for any dynamical system that has some hyperbolicity. So what the theorem says is that if you have one of these generalized U-Gibbs states, so measures that have some kind of non-trivial invariance, then essentially one of two things happens. So if it satisfies a certain condition, which I'll detail in a moment, then it turns out that it has invariance under a larger subgroup. So you can kind of keep growing the invariance. So it's kind of a dichotomy. It says either you don't satisfy, so this is kind of a double negation here, so it's kind of confusing, but you either don't satisfy Q and I, or you can increase. So you can kind of imagine you keep applying this until you reach the point where you don't satisfy this quantitative non-integrability. So then you reach a point where you can start drawing some conclusions about the measure. So what is this Q and I? It says that, again, I'll have to draw a picture. So it says that if you have your Q, this is its unstable, this is its stable. So you can choose points Q, Q prime, and here. So what I want is I want this U plus that goes out of Q prime. I want it to kind of miss the center stable manifold of Y. And if these distances are roughly of the order R, then I want this thing to, the distance between them to be at least some R to the, say, alpha naught, yeah. So alpha naught could be enormous, but you want them to some high order, you don't want them to meet like that. So essentially what would happen is that if your measure was supported on a submanifold, and your U plus contained all the unstable directions of that submanifold, then these things would start meeting, and you would have this, you would be able, these things would be stuck in a smaller submanifold, and so they would meet. But so this basically, again, there's this kind of double negation, which says that if you keep applying the theorem, when you can no longer get extra invariance, you get that your U plus is very large, and so large that it keeps meeting this center stable manifold very very close. So you would expect to be able to kind of construct a submanifold to which the U plus is confined, and the center stable manifold will also have to kind of. So basically, you would expect that these two things should intersect for dimension reasons. Yeah, maybe I'll say this: if U plus is fully dimensional, and this is fully dimensional, then these are two manifolds of complementary dimensions, which point kind of in such a way that they would have to intersect for dimension reasons. But in general, if U plus is too small, then of course it doesn't have to meet this. Okay, so you probably, I hope at least you understand why I started with a simpler theorem in the beginning, because I realize this is kind of a fairly technical result, but it's one that you can keep applying, and if you combine it with other tools, then you reach a point where you have some good understanding of what this mystery measure nu looks like. So let me just say maybe a few things about early work on these kinds of results. So there's a technique introduced by Benoit and Kahn called exponential drift, and so they considered random walks, but on homogeneous spaces of the form G mod gamma that we talked about earlier. And what was particularly important about their work was that they could treat the case where each of the diffeomorphisms Fi in that random walk were hyperbolic elements. So if you allowed at least one of the diffeomorphisms to be a unipotent transformation, then you could use things like Radner's theorem. But if you have hyperbolic elements, then people didn't know how to do this, and it was kind of Benoit can't really manage to obtain a kind of a full analog of Radner's theorem and these kinds of quotients. And then it was subsequently generalized to a space which is not exactly a homogeneous space for a Lie group, but still has a homogeneous structure. So it was generalized by Alex Eskin and Mario Mirzakhani for the action of the group SL2R on moduli spaces of translation surfaces, so something having to do with Riemann surfaces. But as a dynamical system, it's something, again, that has some kind of local homogeneous structure. Then Aaron Brown and Federico Rodriguez Hertz extended some of these results for random walks on surfaces. So when the manifold Q is a real two-dimensional surface, then Eskin and Lindenschaus kind of used many of the ideas that were kind of introduced by Eskin and Mirzakhani to go back to the case of random walks on homogeneous spaces. And Cantat and Dujardin considered the case of complex projective surfaces.
So, sorry, Simion, what's the difference between Eskin Lindenstrass and Benoit Kant? Because it seems like
yeah, so I think
G-mod gammas.
Yeah, so they're both G-mod gamma. I think it's in the assumption. So I think Benoit Kant need to assume Zariski dense or close to Zariski dense. And I think, and also maybe G has to be semi-simple. So where's Alex? And also you have two papers also. So, so I think in the second one, you don't need to assume Zariski dense, but also the Zariski closure is not necessarily semi-simple, I think.
Yeah, that it's just variance in this. I mean, different assumptions, different conclusions.
And
Slightly
then
different methods, yeah.
Rodriguez Hertz, the surface could be variable negative curvature then?
Oh no, so the surface is just a topological surface. So you're just diffeomorphisms of a general compact surface. So there's no, I mean, the Riemannian metric plays no role for the diffeomorphisms. Okay, so let me say a few words about what you can do with such a theorem. So, as I mentioned when I showed you the statement, you apply it inductively until you reach the point where Q and I no longer holds. So then, at that stage, you would hope that under some additional assumptions, the measure nu is some kind of Lebesgue measure on a submanifold of your ambient manifold Q.
Nu is the same as mu in the theorem?
No, nu is the measure on the manifold. So this is the measure on the manifold.
What was the mu?
Mu is the measure on the diffeomorphism group. It's the random, like the probabilities of the individual diffeomorphisms. Is there a mu? So I think this is correct, but it's possible that in some earlier slides it was going to
So you wrote QG mu, and now you're saying nu? So it doesn't matter.
Sorry, yeah. I did change at some point the mu's and the nu's, but it was a long time ago, so it's possible that one of them persists, but I think this is... So nu is on the manifold, and mu is on the group. So at this stage, you expect that it's Lebesgue measure on a submanifold. Now, on the theorem on the first slide, the assumptions were of such nature that this submanifold basically had to be either a point or the whole ambient manifold. So at that point, at this stage, you don't have to kind of find the manifold. It's just kind of there. In general, the place that the theorem brings you to is that you have a good guess for what the tangent space could look like, but you still need some additional assumptions to exclude things that could go wrong kind of in the normal direction. So you could always kind of imagine a situation where you take a nice manifold on which things are nice, but then you take a product with something like this counter set example that I gave initially, and you could have a measure could be nice in one direction and bad in the other direction. So somehow at the point where this induction stops, at least you expect that all the directions that you found have Lebesgue measure, and transversely, you either want to eliminate it by assumption, or you just don't want to say anything about the transverse measure. So there's some arguments having to do with entropy, which I haven't included here, but again, they have to do with this basic feature of dynamical systems that somehow the same dynamical system, entropy, which is this kind of measure of complexity, for the future dynamical system and for the past, they're the same. So this is kind of a rather kind of surprising fact from one point of view, because this entropy is closely related to the Lyapunov exponents and with the measure in these conditional measures. And so basically the Lyapunov exponents in the stable direction, in general, they have very little to do with the Lyapunov exponents in the unstable direction. There's some basic constraints that they might have to satisfy, but in general, they're just, two things. And this entropy of the future equals entropy of the past tells you that they have to satisfy certain balancing that, it ends up being extremely powerful to deduce many consequences. So you'll notice kind of one thing that I did, which is that I told you a theorem for a general flow on a general manifold, but then I keep referring to a situation where you're doing a random walk on a specific manifold, and it turns out that there's a nice analogy between the two situations, and you can transfer theorems and proofs from one direction to the other. And what you have to do is you have to think of the random walk as a one-parameter system where you have your manifold Q, and the base is you take the group of diffeomorphisms, sequences of diffeomorphisms. That's your base space, and the dynamics is given simply by shift and acting on the fiber by the diffeomorphisms. So once you're in that setting, you can essentially get the theorem that you prove in, for one parameter flows. You can get some theorem in this case as well for random walks. In these random walk settings, again, there's an analog of this Q and I and Gibbs states. And the invariance that comes in the first on the first slide is related again to entropy. And as I mentioned, one of the things that I made at the start is that the hypotheses were such that these intermediate submanifolds simply were not allowed to exist. In general, for more interesting examples, we expect that there should be such possibilities, but then more work is needed to kind of reconstruct them. A lot of the these dynamical systems that we're considering, what's interesting about them is you can also take products of, so if you have Q and a random walk on Q, it makes sense to take, say, a product of Q with itself and consider the joint random walk. And oftentimes this can actually tell you interesting things about the original random walk as well. So it's a general technique in dynamics where you can relate properties of the original system with properties of the self-product. And in particular, we can, one consequence of these earlier results is this measure classification for the action on products of strata. This is kind of a cheap application because it could have been obtained essentially by Alex and Mariam when they wrote the paper, but they just didn't. So it's not, somehow all the techniques are there as well. Okay, so what can you possibly use this for? So one thing is that this Q and I condition, which I didn't give you, I only kind of gave you a very impressionistic view, it should, under appropriate assumptions, it should allow you to find these intermediate submanifolds. So try, the integrability of these foliations, plus probably some other assumptions, should really lead to at least germs of these submanifolds in which the measures should live. And this property of uniform expansion, again, it should have analogs that are kind of a little bit weaker than requiring it at every vector, but maybe requiring it of some submanifolds. And it's also related to kind of an interesting feature that arises in Hodge theory, which is the fact that norms of certain vectors are subharmonic. So just to remind you, what's a subharmonic function? So a harmonic function is one that for which the value at the center of a sphere is equal to the average over any sphere. So a subharmonic function is simply one for which the value in the center is less than or equal to the average over any sphere. So, so it's a little bit like uniform expansion, right? It says you take a vector, if you imagine it's moving out by the random walk, you take the average over that place where it landed, then you want it to be a little bit larger than what it started. So you have this kind of subharmonicity in Hodge theory, And in particular, we hope to eventually prove much more detailed theorems for the action of the mapping class group, and not just the mapping class group, but in fact subgroups of the mapping class group that come from families of Riemann surfaces acting on character varieties. So these are varieties of representations of the fundamental group into compact V groups. So these are some compact manifolds with a nice action of some nice, in appropriate coordinates, nice polynomial automorphisms. So for these, we hope eventually to have some classification of orbit closures and invariant measures. And what I think will probably be most useful is the fact that we don't need to take the full mapping class group, but in fact, monodromy groups of any algebraic family of Riemann surfaces should satisfy the same kind of properties. Another feature of many of these theorems, and especially their hypothesis, is that they're valid for any perturbation. So if they're valid for one system, they're valid for small enough perturbations of those diffeomorphisms that generate the random walk. So in particular, if you start with a homogeneous example, if you perturb it to general smooth diffeomorphisms, the same conclusions continue to hold. In general, these kinds of uniform expansion conditions, most of the time the reason why we know they fail are for some kind of natural geometric reasons. So I think it's fairly natural to hope that maybe there's some kind of fairly robust criteria for when a bunch of diffeomorphisms satisfy this uniform expansion condition. So in the case of matrices, such conditions exist, and they have to do with this theory of Furstenberg of random products of matrices in SL and R. But in general, one can hope to have something analogous for general diffeomorphisms of manifolds. So knowing when, to say it differently, it's very hard to kind of fail uniform expansion. So far, the only way we know it fails is for some kind of very obvious geometric reason. So, maybe there's some kind of, it's either true or not kind of thing. It should be a very verifiable assumption. Is the upshot. The other aspect of it is that the Spain theorem, as I said, it applies to any one parameter system of one parameter flow on a manifold. In particular, for example, to Anosov flows, which in general were not thought of as something particularly rigid. And so we would hope to generalize the following theorem that I mentioned, I'll end with, which is joined with David Fisher and Ben Lowe. So the theorem is the following. If you have a closed and negatively curved analytic Riemannian manifold, at least of dimension at least 3, and if it contains infinitely many closed, so the word closed here is missing, immersed totally geodesic hypersurfaces, then actually the conclusion is that this M is isometric to an arithmetic constant curvature hyperbolic manifold. So there's maybe a better way to say it, which is that if you're not isometric to a constant curvature manifold, you have only finitely many totally geodesic surfaces. So in this form, it's a theorem that applies to all negatively curved Riemannian manifolds, namely, they only have finitely many totally geodesic hypersurfaces, unless they're homogeneous. So there's two hypotheses here that we would like to drop. One is the condition of being analytic, so it should be smooth, and the other one is hypersurfaces. But again, the trick here is that when I assume hypersurfaces, this kind of rules out any intermediate possibilities. In general, you should say for any k at least 2, if I have infinitely many totally geodesic k-dimensional submanifolds, they should be accounted for by a homogeneous subspace of M. So M should contain rank 1 locally homogeneous negatively curved manifold, which accounts for these totally geodesic hypersurfaces, not hypersurfaces, but submanifolds. So the hypersurface hypothesis excludes this intermediate behavior, but in general, you have to produce somehow these submanifolds, and we would hope that these techniques about these invariant measures should eventually yield, for example, these kinds of theorems. All right, so that's all I have to say. Thank you.
Questions?
Can you give a specific example of a manifold where your main theorem apply and illustrate like the Q and I condition and stuff like that, for example?
Well, one simple example is if you take T2 and you take two matrices in SL2Z, that generate as a risky dense subgroup, and then you just put small diffeomorphisms in each of the 2 by 2. You have each matrix has 4 entries. You just put smooth diffeomorphisms in each of them, which just keep the determinant 1 in each of them, and so then the main theorem will apply. And in that case, yeah, somehow things like this Q and I condition don't appear. I mean, the conclusion will simply be it's either the orbit of every point is either finite or dense in the whole. Does it make sense? Or?
Yeah, to a degree.
About this Q&A condition, when you apply it iteratively to get the submanifold S, do you have the control of how S looks like?
So in general, as I said, we don't quite have the full submanifold yet. We have only kind of a tangent space to that. So yeah, so I mean, in some sense, these U plus directions are really what kind of determine which directions you will see the submanifold. So, I mean, I was just saying, when the Q and I condition fails, it just tells you that the U plus and the center stable they approach each other very well. But you can define a subspace of the at each point, which essentially is the span of all the possible U pluses that you can see, and that is kind of the hypothetical, at least, tangent space to the manifold. It should carry the measure.
Yeah. You said that like one of the crucial points is that your theorem holds under smooth perturbations of your dynamical system. Are you able to control qualitatively or quantitatively like the associated like Lyapunov spectrum for the dynamical system as you perturb it?
Well, so I mean, I think in general, basically C1 perturbations should be enough, at least to have uniform expansion, for example, right? And if the size of the C1 perturbation. So the uniform expansion assumption gives you lower bounds on the Lyapunov exponents, and if you perturb it a little bit, the size of the perturbation will tell you, by how much at most the quantitative things have changed.
So in this result, how does the central manifold affect the result?
The what, sorry?
So you have this decomposition, the stable, unstable, and central manifold. So how does the central manifold plays a role?
How does what? Sorry?
It's the central manifold.
How does it play a role, or?
Yeah, play a role in this result.
Well, so there's two things. So it appears in the Q and I condition, right? So it says the U pluses. So you can imagine an extreme case. Your manifold is 100-dimensional, and your stable and unstable are each 1-dimensional. So then the center is basically almost everything, like 98-dimensional. Right. So then you have a fairly this Q and I condition becomes it's saying something. It's telling you that these 1-dimensional unstable manifolds, they have to kind of touch this codimension 2 submanifold instead of a codimension 1 submanifold. So it puts a heavy restriction on how the unstable manifolds can look like.
Okay, let's thank our speaker again.